Artificial intelligence runs on mathematics, and at its heart lies linear algebra. But linear algebra is not just theory, it is the practical toolkit of AI. Vectors describe features like a snapshot of important details. Matrices perform transformation, shaping and manipulating data. And tensors capture the complexity of real world and high dimensional information. Once you grasp this essential, you will begin to understand how AI truly thinks at its mathematical core. In the coming slides, please let us discuss this more. A vector is simply a list of numbers, but it carries both size and direction. For example, in finance, a vector like 1200, 800, 500 could represent monthly spending on food, travel, and healthcare. In healthcare, 72, 120, 98.6 might capture a personal heart rate, blood pressure, and body temperature. Vectors are powerful because they capture the key features of an entity, making them the basic building blocks of machine learning. We can do simple yet useful operations with vectors. Addition, let us combine features. The dot product measures similarity, which is useful in recommendation systems. And scaling allows us to amplify or shrink values. With tools like NumPy, these operations are easy to perform in just a few lines of code as shown here. A matrix is like a table of numbers arranged in rows and columns. It helps organize information and perform transformations. For example, in retail, a matrix can store product sales across different months. In computer vision, an image is just a matrix of pixel values. And in analytics, we often use a user item rating matrix to recommend products. Matrices are extremely important in AI because they power neural networks where inputs are multiplied by weight matrices to make predictions. Some key operations with matrices include transpose, which swaps rows and columns, multiply, which combines data and parameters. This is the core of machine learning. And inverse, which helps solve systems of equations. With tools like NumPy, these operations are easy to run in just a few lines of code as shown here. A tensor is like a big brother of vectors and matrices. While vectors are one-dimensional and matrices are two-dimensional, tensors extend into higher dimensions. For example, a color image is a 3D tensor with height, width, and RGB channels. When we process a batch of images in deep learning, that becomes a polytensor. And in healthcare, an MRI scan can be seen as a 3D tensor made of layer slices. Tensors allow AI models to handle large multidimensional data efficiently, making them the backbone of modern deep learning. With libraries like NumPy, we can easily create and work with tensors in just a few lines of code as shown here. Linear algebra is the backbone of artificial intelligence. It helps represent data, whether it is text, images, or audio, using tensors. It powers computation since neural networks are built from layers of matrix multiplications. It enables optimization using vector and matrix calculus to train models. And it provides scalability with GPUs accelerating massive matrix and tensor operations for deep learning. In short, the elegance of linear algebra transforms raw data into intelligent insights, making AI not just possible but more powerful. Let us see how linear algebra powers face recognition step by step. First, the input image is processed. It represented as tensor, capturing height, width, and color channels. Next, a neural network takes over. It uses matrix multiply and transformation to extract unique features from the face. These features are then stored as vector in a high dimensional space. Finally, when comparing two faces, the system measure similarity using dot product of their feature vectors. In simple terms, linear algebra transform raw pixels into meaningful patterns, allowing AI to recognize faces with impressive accuracy.